All right, welcome back. We're going to pick up where we left off. Last time we talked about titrations. We talked about strong acid titrating with a strong base. And the thing that you need to remember about a strong acid with a strong base titration is it's the hydrogen ion or hydronium ion, if you want to write it out formally. But it's the hydrogen ion from the acid reacts with the hydroxide ion of the base, and that forms water. And so once we've added just enough base to consume all of the acid, the equivalence point would occur right at pH of 7 because that's what the pH of pure water is. Then we talked about the titrating a weak acid with a strong base. And when we do that, what happens is uh, yes, the hydrogen ion gets consumed by the hydroxide ion, and that forms water, and that would be a pH of 7. But the conjugate base of the weak acid will react with water, and that forms the molecular weak acid plus the hydroxide ion. So that makes the pH a little bit higher than 7. So the equivalence point for a uh, weak acid with a strong base, the equivalence point was a pH greater than 7. All right, so that's the hallmark right there, greater than 7. It's going to be basic. And the reason why is because the conjugate base undergoes hydrolysis with water and forms the weak acid, the molecular form that it wants to be in, plus the hydroxide ion. So this lecture, we're going to pick up from that. We're going to be dealing with a strong acid with a weak base. Strong acid with a weak base. So let me clean this up a little bit. Let's just, oops, I thought it would, I guess not. Let's see. Does this work? Oh, there we go. Let me just erase some of this so we. All right. So what I want to talk about is okay. Think about what a strong acid is with a weak base. Give me an idea of a weak base. What's the most common weak base that we use? Well, that'd be ammonia, right? So you have ammonia, and you're going to react that with a strong acid, which is, we'll just say the hydrogen ion to represent the strong acid. And this reaction is going to go like this. Okay. And so this is the conjugate acid of a weak base. This is my weak base. There's the conjugate acid. So once this is formed, then that's going to react with water. So if we add water to this, and we're going to form ammonia, and that'll be double arrows because it's an equilibrium, plus the hydrogen ion. So it's going to make the equivalence point, since hydrogen ion is left at the equivalence point, notice the equivalence point is less than 7. So for when you have a strong acid with a weak base, the pH is going to, the equivalence point is going to be at a pH less than 7. So that's what you're supposed to get out of this section. And again, why is this important? Because when you're doing titrations in the lab, you need to know, is it a strong acid with a strong base? Is it a weak acid with a strong base? Or is it a strong acid with a weak base? And knowing what the equivalence point is gives you an indication of what we're working with. So again, notice it looks, all these plots, what you're doing here, again, let's talk about what's happening. You start off with 0 of the titrant added, and in this case, the strong acid is the titrant, and the substance in the beaker or flask we call the analyte. And so initially, the Erlenmeyer flask has just weak base in it, and the pH is 11.13. We start adding acid to the flask, and we notice that the pH starts to drop. But when we've added just enough acid to consume all of the hydroxide ion, or the ammonia in this case, the equivalence point tells us the pH is less than 7 because of this reaction here. And then once we, at that point on, the pH drops very quickly because there's no ammonia to react with the acid. There's no ammonia to react with the acid, so that's why the pH drops drastically from here on down. So that's what we're doing, and then you're recording. You've got this in a pH. You're taking the pH at these different points. That's what these dots represent. And again, notice there's more dots here and here because that's where the dramatic change is as we go through the inflection here, the equivalence point, which you call an inflection point, and so that's what we're focused on. All right, so let's see what's going on here. Okay, so our next slide, that's what they chose, and I just lucked out. So again, it's a strong acid with a weak base. It forms this compound. Notice I didn't put the chloride ion in my reaction because it's a spectator ion. It doesn't react with. What we learned in the last chapter was chloride ion does not react with water and form hydrochloric acid plus the hydroxide ion because this is the conjugate base of a strong acid, hydrochloric acid. So this reaction does not happen. So the chloride ion is a spectator ion. So really what I'm interested in is the hydrogen ion comes in here, reacts with the ammonia, and forms the ammonium ion. They show it more formally, and I like the formal application of it. Really, it is the hydronium ion, but shorthand, you're going to write it like I wrote it, which is hydrogen ion, the acid, reacts with the ammonia to form the ammonium ion. All right. So here we have, it says the pH at the equivalence point is less than 7 because at the equivalence point, you have just the ammonium ion and it will react with water. And again, this is a fairly strong acid because it's it comes from the weak base ammonia. The weaker the base, the stronger the conjugate acid. And so the ammonium ion is going to donate a proton or hydrogen ion to the water, form ammonia, and then it generates the hydronium ion, and that makes the pH less than 7. Pretty much just a summary of what I just said in the last one. All right, so again, ice table. So ice table, before the equivalence point, okay, so you got to define when you're doing this in a titration. Before the equivalence point, at the equivalence point, after the equivalence point. So before the equivalence point, you have 25 milliliters of 0.1 molar ammonia, and you're adding 0.10 molar hydrochloric acid. So initially, you have just ammonia, and ammonia is they've made a typo here. Well, no, it's okay. So the ammonia is here, and then the water acts as an acid, donates a hydrogen ion to the ammonia, and that forms the ammonium ion. So initially, all you have is ammonia. Water, again, a pure liquid, not in the expression. It's integrated into the constant itself. I should say it that way, not in the expression. It's integrated into the base ionization constant. And initially, these are 0, the ammonium ion and the hydroxide ion. Since these are 0, we know, again, always remember Q, reaction quotient is less than K, so reactions, because it's 0, right? So 0 is less than K. We know the reaction is going in the forward direction. That's how we know this is minus X, this is plus X, and this is plus X. And again, one thing I want to stress here again, these are all minus X because the coefficients in front of these substances are 1. If it was a 2 in front of here, then you'd put a 2X there, or 2X here, right? But it's not, it's 1, so don't worry about it. So here's my equilibrium values. This is an ice table that we've been doing over and over again from chapter 15. So we plug this into the basicity expression, and we know this is a base constant because, again, the hydroxide ion's in the expression. That's what tells me this is a Kb. I plug in the values. We assume this X is negligible. We solve. We set that equal to the Kb that we find in the table. You should know how to read the table. Make sure. I'm not asking you to memorize the Kbs, but I do expect you to look at a table or take a word problem and pull that out of that. Solve for X. Take the square root of both sides, and we get 1.3 times 10 to the negative 3. We take the negative log of this, and what do we find when we take the negative log? Be careful. You found the POH, not the hot pH. And that's where I find students make a mistake here. You're solving for this, so this is POH. Then you subtract that number from 14 and you get the pH. Make sure you make that step there. How do you make sure you do this correctly? Because you write the expression up here and you don't see hydrogen ion or hydronium ion. You see hydroxide. So you're solving for POH, not pH. Make sure you do that. I see so many students miss that. All right. So then that's what the initial pH is. Okay. Then at the equivalence point. At the equivalence point, the ammonia is consumed, and what you have is ammonium ion. All right. So let's look at the table here. On the table, and we can talk about that, but let's just go on and look at it here. Yeah, they jump right to the problem. I think they should have talked a little more about this. Okay, but let's look at it. Calculate the pH at the equivalence point when 25 milliliters of 0.1 molar ammonia is titrated with 0.1 molar hydrochloric acid. So, what's going on? You got the ammonia, you got the hydronium ion, the ammonium ion in the water, and the first thing, and this is where I find students make a mistake too, you have to determine the concentrations. So I see a lot of students just take the 0.10 and say that's moles. No, that's moles per liter. And initially you have 25 milliliters of the solution. And you know that when you titrate this, since it's a 1-to-1 ratio between this and this, that when you get to the equivalence point, you're going to have a total of 50 milliliters of solution and not 25. So that's where I see students make a big mistake, is that originally I agree it's 25. I mean, this is, draw a picture. Draw you a line like that, and there's my burette. And then you don't want to use an Erlenmeyer flask, you can use a beaker. But what you know is initially, excuse me, you have 25 milliliters of 0.1 molar. So if I multiply those, I get 0.1 millimole per 25 milliliters. All right? So if I multiply this times this, I get 2.5 millimoles, all right? 2.5 millimoles of ammonium ion when the titration's done. Yeah, let's work that out just to make sure. All right, so we have 25 milliliters, right? 25.0 milliliters. And they're telling us that we have 0.100 millimoles per milliliter. Milliliters cancel out. Excuse me. And that gives me 2.50 millimoles of ammonia. All right. So then we've added enough of this to convert all of this into that. So at that point you have 2.50 millimoles of this. But here's where the mistake is made. That is divided by 50 milliliters of solution to get the concentration. Because you had the 25 and you added 25 milliliters of hydrochloric acid to convert all the ammonia into the ammonium ion. All right, I hope you think about that. Just make sure you understand what's going on. All right, so that's what they're showing here. You need 2.5 millimoles of hydrochloric acid, and this is the concentration of the hydrochloric acid. So, I mean, we already figured that out, right? That you need, since they both had the same concentration, both were 0.1 molar, we knew that you needed 25 milliliters of hydrochloric acid. But they formally show you that calculation here. And then they get to what I said. The total volume is now 50 milliliters. The 25 that was in the container to begin with the ammonia, and now you're adding 25 more to neutralize all the ammonia to make it ammonium ion. All right? So it's so important. They do a whole slide on it here. So I can't stress that enough. That's where most students make a mistake. You got to take the volume that you have plus the volume that you added to determine the new concentration in your flask or beaker in this case. All right, so here's my ice table. Notice the ice table's changed. The ammonia is consumed. The hydrochloric acid is consumed. So what we have left at the equivalence point is just the ammonium ion in water, and we know that this is the conjugate acid of the weak base ammonia, and ammonia wants to be in its molecular form like this. And initially this is 0, and initially the hydronium ion is 0. So we know that Q is going to be less than K because Q is 0, and that's going to be less than 0. So this reaction is going in a forward direction. We're going to lose X amount of the ammonium ion. We're going to gain X amount of the ammonia and X amount of the hydronium ion. So our equilibrium values are this. We're going to plug this into an equation. And here's the question before I flip to the next slide. Do I need a Ka or a Kb? It's going to be a Ka. Why is it a Ka? Because all Kas, acid ionization constant expressions, have the hydronium ion in the expression. This one does not have hydroxide ion. It's got the hydronium ion, so it's a Ka. So you're going to look up the Ka for the ammonium ion, and from the table, that's 5.6 times 10 to the negative 10th. And you go, I don't see the Ka for the ammonium ion. Well, then this is what you got to remember. Here's a tool that we talked about in the previous chapter. Ka times Kb has to equal 1 times 10 to the negative 14th. That's a tool. So if I need the Ka, I would take the Ka equals 1 times 10 to the negative 14th, and I would divide that by the Kb for ammonia, which is 1.8 times 10 to the negative 5th. Is that what it was? It's on that last slide. But that would come out to be this number here. All right? Now, these are all nice because we get to say, here we didn't have any of this to begin with, so it's not, we assume the X is negligible there, and we can throw that out. This is a typo. This should be down here. We're going to throw that out. We get this. We solve for X. We take the square root of X. We get this number. What is that number? Is that pH or POH? This one's pH. All right. I mean, when we take the negative log of that, this is the I should say this. This is the hydrogen ion concentration. I'm going to take the negative log of that number, and I will get the pH. Why do we know it's not pH, not POH? This is what you're solving for. So here you are solving for pH. The other one you're solving for POH. So at the equivalence point, the pH is 5.28. Notice it's less than 7. That's what happens when you titrate a weak base with a strong acid, or a strong acid with a weak base, either way you want to say it there. That's at the equivalence point, and the key here is the pH is less than 7 and the solution is acidic. Why? Because the ammonium ion generates the hydroxide ion. A good problem. I like that one. All right. So then we talk about acid-base indicators. So probably in the lab, I don't know if everybody used a pH meter. You should, but you probably also did a titration with an acid-base indicator. All right. So acid-base indicators generally change color. They're generally weak organic acids or bases, and whether it's ionized or unionized, it has different colors. So ionized has one color. Unionized has another color. So what makes it ionized? Well, when you take a hydrogen ion and it attaches itself to this substance, this indicator, maybe I should have used I here, but now we have an ionized form. So this will have a different color than this color unionized. So when we see that color change occur, that's when we say, oh, well, we've got to stop our titration. So the one that you see a lot of is phenolphthalein. So phenolphthalein is colorless when it's ionized. It's colorless. And so we like that. And then when we take the hydrogen ion off of it, it becomes pink in color. So we're kind of seeing the reverse of this. We have an acid that's colorless, an ionized substance, and then as we add base, the base takes the hydrogen ion away, and eventually we just have A. And when we have A, it changes to pink. So that's what we're looking at here. All right, so they draw it for us. Here it is. Here is the molecular indicator. We have it in water. And then that molecular indicator can ionize into the hydronium ion and the conjugate base, ion negative. Over here, it's acidic. Because it's acidic, the hydrogen stays in the molecular form on this indicator, and so that's acidic. But if we add base, the hydroxide ion consumes the hydronium ion, and this reaction shifts this way to make up for that loss. And we have the conjugate base of the indicator, and that's going to have a different color. So I want you to know the difference between equivalence point and endpoint. Endpoint is when the color changes. Now, you hope that the equivalence point and the endpoint are pretty much the same thing. You want to choose an indicator where the equivalence point occurs. That the range of the indicator is where the endpoint occurs. But endpoint, again, is just a color change. Equivalent points is kind of theoretical. It's where you've just added enough acid to neutralize the base. And so we can do it by calculation, but it is, for the most part, it's more of a theoretical point than it is an actual applied point. So endpoints where the color change occurs. And it says, we select an indicator whose color change occurs over the pH range that coincides with the steepest part of the titration curve. This is really important here. This is how you determine which indicator you're going to use, that where the endpoint will change, the color will change when the steepest part of the titration curve changes. And if you don't get that correct, then you don't see a color change through the course of your titration. You're going, it's not working. Well, you chose the wrong indicator. All right, so let's show you how titrations indicators work and how we use that to determine where we see a change that hopefully indicates where we pass through the equivalence point. So we're looking at this titration. And what you're going to see is there's a blue titration and there is a red titration line. And so what's the difference here? So the blue titration, can you figure it out? Which one is it? Is it the hydrochloric acid or the acetic acid titration? See if you can figure that out. Because if you can, that means you have a pretty good indication of what's going on. So this one is the hydrochloric acid. So this is hydrochloric acid being titrated with sodium hydroxide. And you go, how do you know that? Well, you look at where the equivalence point is. That's going to be about midway on this steep curve. And so the red one, it's somewhere up in here somewhere, right? I mean, if you think about it, it's about halfway. It's somewhere like here. That's what I would guess, about halfway. So this one must be the acetic acid titration curve. So when we're looking at these indicators, we want the indicator to change color in the steepest part of the curve. So I agree that this is the one we mostly use for strong acid, strong base. It's readily available, easy to manage. It's got a very distinct, goes from colorless to pink and happens fairly quickly. But the methyl red would work as well, right? Because it would go from one color here to another color here. It's just that sometimes it's a little harder to see that color change. And so we generally use methyl red. We generally use phenolphthalein for hydrochloric acid with sodium hydroxide. For the acetic acid, this is the color change is occurring in here, right? It's not in the steepest part of the curve. It's not even close to the equivalence point. So methyl red would be a bad choice for the acetic acid because it's not, the color change is occurring not in the steepest part of the curve. Either one would work for hydrochloric acid and sodium hydroxide, but we generally use phenolphthalein. All right. So let's see. And that's pretty much what this says. Methyl red is not suitable indicator for the acetic acid. So here's the color changes. I'm not asking you to memorize these. What I'm asking you to do is I want you to choose the best indicator for the titration you're doing. So here's the pH ranges. So if you're dealing with something that's going to change the equivalence points in the acidic region, then you're probably going to choose something maybe even down to here, although that one's a little iffy, but you're going to choose something down here. And if the equivalence point is in the, pH above 7 region, then you're probably going to choose one of these two here. All right, so phenolphthalein changes here, which is above the equivalence point of 7, but it's still in the steep part of the curve. So phenolphthalein is not perfect, but it works pretty well. And let me show you the calculation for that. So how do you know which indicator to choose? So I'm not asking you to memorize any of this on this page. I'm asking you, if I gave you a table like this, you could tell me which indicator would be the best choice. And there's a way to do that. It says, which indicators would you use for the following acid-base titrations? So the steep part of the curve spans 4 to 10. For B, it's 7 to 10, and for C, it's 7 to 3. So look at where this steep part of the curve is, and then choose the best indicator that is in that steep part of the curve. All right, so we're looking at this. I'm not asking you to memorize it, just be able to interpret it. And so most indicators, with the exceptions of thymol blue, bromophenol blue, and methyl orange, would work. All right, so let's go back. It says where the pH ranges from 4 to 10. 4 to 10. All right. So we're looking at, thymol blue wouldn't work, right? This is happening way before that. And then they're telling you that creosote red and would not be the best choice as well. So it says thymol blue, bromophenol blue. All right, let's go back and see where bromophenol blue is. 3 to 4.6, and our pH is 4 to 10. Yeah, this is happening before we get to even 4, right? So that's why you wouldn't use that. And then, interesting, methyl orange. Let's see where methyl orange was. Methyl orange, again, starts before 4, and that's why they're not choosing those. And I guess these do work because they happen before we get to they happen before we get. So let's go back, and it says the 4 to 10. So 4 to 10, this one's occurring at, so we're not exceeding that. So that's why these two actually do work, the creosote and phenolphthalein. It's probably not my best choice, but I can see why they chose that. All right, so let's look at the next one. Creosote red and phenolphthalein are suitable indicators. All right, so let's look at that. pH range of 7 to 10. Creosote red, 7 to 10. That looks pretty good. And then this one too. Either one of those would work there. These are happening too early. These are happening way too early for that. All right, last one. Bromophenol blue, methyl orange, methyl red, chlorophenol blue. So let's see what the range was. 7 to 3. So we're going from a 7 to a 3. 7 to 3. And so we're going like this, and we're going down like that. And we're looking for something in this steep part here. 7 to 3. Yeah, right in here. Bromophenol, methyl orange, methyl red. Yep, and that's what we have there. All right, so be able to do a problem like that, just choose the right indicator for the right. The main thing is the indicator has to be in the steepest part of the curve, all right? Not in the flat spots. It's got to be in the steepest part. All right, next we're really switching gears here. We're still dealing with equilibrium. We are exiting talking about acids and bases, acid-base titration, and we're going to talk about solubility product. So I'm going to stop here, and then we will pick up on this on the next lecture. So because we're changing gears from talking, we've been talking about acid bases for the last chapter and a half, or chapter half or so. So now we're going to talk about solubility, like when we're adding the titrant to the analyte and it causes a precipitation reaction. So we're changing gears. All right.